Welcome to this lecture series in real analysis. Last time we defined what are rational numbers, and in this lecture we'll define a notion of ordering on them. It is the same notion of ordering that we are already familiar with from high school, but we will do things formally. So let us recall a little bit. So in my primer on posets, I have defined what is a partial order and what is a poset. Poset stands for a partially ordered set. That video is available in this playlist as well as in the playlist named Kickstart. Let me write that down. And you can find them in the description below. Now let me define what is a total order. So a total order is a special kind of partial order. A total order on a set P is a partial order such that for any two elements A and B in P, we have either A less than equal to B or B less than equal to A, or both, which happens only when A and B are equal. So that is a total order. And we saw that the integers have this property, meaning the ordering on integers is actually a total order. So an informal way of saying this is that a total order on P is a partial order where any two elements are comparable. So if you define comparability as one of these relations, then it's not an informal way of saying it. All right, so that's a total order, and a totally ordered set is just a partially ordered set where the partial order is actually a total order. This may sound like garbage, but it is actually a very meaningful mathematical statement. So for instance, this is a total order, the ordering on integers. The usual ordering on integers is a total order or a totally ordered set. The integers is a totally ordered set under the usual ordering. All right. Okay, last time we defined rational numbers. We defined a set S, which was all pairs of integers of the form where the second one is non-zero. And then we defined an equivalence relation on the set and quotiented that out to get Q, meaning we collected all the equivalence classes to get this set of rational numbers. Okay, and we saw that for each rational number, we can write it in this form A by B, where B is positive. B is a positive integer. A is an integer and B is a positive integer. Very simple fact. And lastly, we looked at how to identify integers inside the rationals. The identification was very, very simple. You just think of an integer as this particular rational number. Okay, so let us now move on. So we will define an ordering on Q, meaning a partial order on Q, which will turn out to be a total order. So how do we do that? So let alpha and beta be in Q. Say alpha is equal to A by B and beta is equal to X by Y, where B is positive and Y is positive. As we just recalled, one can always express any rational number in this fashion, meaning where the denominator is positive. And yeah, of course, A, B, X, Y are integers. Okay, so suppose we express alpha and beta in that way, then we define, we define alpha less than equal to beta if and only if AY is less than equal to BX. So this symbol is talking about the integers. So this symbol and this symbol are actually different. They look the same. This is what we are defining, while this one already exists. We are just borrowing the ordering on integers to define an ordering on Q. These are integers. A, y, and bx are integers because they are product of integers. So this just is the same ordering on integers that we are familiar with. Okay, so that is the definition of this symbol. That is just a relation on Q. So what one would like to do is to check that. Check that this thing is reflexive, antisymmetric, and transitive so that it becomes a partial order. Let me say a few words about transitivity. So to justify transitivity, how do I do this? To justify transitivity, let alpha, beta, gamma be rational numbers such that alpha is less than equal to beta and beta is less than equal to gamma. We want to show that alpha is less than equal to gamma. Okay, so say alpha is this, beta is that, and gamma is this, where all of these things are integers and the denominators are all positive, and I have run out of space. So now we have, by definition, by this we have ay is less than equal to bx, and we have xb is less than equal to ay. So this one comes about because of that, and this one comes about because of that, by definition. All right. So we have ay times b is less than equal to bbx. Why is that? Or let me write it that way. bxb. Why is that? We just multiplied both sides by capital B, and this preserves the inequality because capital B is a positive number. If it were not positive, we couldn't do this. Okay, so we have that. And now this is less than that, right? This is less than that as written here. But since little b is also positive, we see that this is less than equal to b times ay. Correct? So the upshot is aby is less than equal to bay. This and that are same. And we can cancel y off. Again, since y is positive, we cancel off without changing the inequality. So this implies AB is less than equal to BA, which is same as saying that A by B is less than equal to capital A by capital B, which is same as saying that alpha is less than equal to gamma. So it's nothing. It's just some basic high school arithmetic. Okay, so I leave you to check reflexivity and antisymmetry. That is very, very simple. And I also want you to check that this is actually a total order. So this statement says that this guy is a partial order, but check that this guy is actually a total order, which is also a very, very trivial statement. So check that. This is a total order. Okay. And here is something to note. It is just a matter of notation. So for any partial order, suppose we have a partial order on some set P, then we write this for two elements in P, x and y are elements in P. We write this symbol to mean that this is the case and this is the case. So if you have two different elements with some comparability, then you may combine those two statements to write a succinct single statement. Again, we are already used to doing this. And also, one flips this around to mean that. Again, we do this in basic, high school level. And we write that to mean that. Okay, so with these notations in hand, now we can talk about the next thing. So this does define a total order on Q is the upshot. And now this has some properties, most of which or almost all of it will be exercises because they are very, very simple. So let's express them. So this is a notation to denote all those rationals which are positive, which are greater than 0. Again, 0 stands for 0 by 1. All right, so note the two fundamental properties using which you can prove the rest, which we will mention. So the first one is if alpha and beta are rationals such that alpha is less than beta or less than equal to beta, but let's just stick to less than, then this happens for all rationals gamma, right? And second property is that if alpha and beta are rationals such that alpha is less than beta, then alpha gamma is less than beta gamma for all gamma in Q plus. So when you want to preserve an inequality under multiplication, you need to be able to, or you need to multiply with only positive things. Otherwise, the inequality would flip. If you're multiplying with a negative number, then the inequality flips. So these are two basic properties, and you can prove them as exercises. And now, once you have established those two, using just those two, you can establish the rest, or you can do them directly. But these are some very simple exercises about this order relation. All right, so that is one thing out of the way. And lastly, let us talk about the embedding of Z in Q, meaning the identification of Z in Q. So we saw that one can identify Z sitting inside Q via this map, which takes an integer m to this rational number. We saw these two properties hold, meaning the map phi respects the addition and multiplication. So essentially, as far as the arithmetic of integers is concerned, one may just be content only with the rational numbers and think of these numbers as integers. But moreover, we can easily prove that it also respects the ordering. So this identification of Z inside the rationals is pretty tight, and therefore, for all intents and purposes, the integers are sitting inside rational numbers. Everything that you can do with integers, you can do just thinking of them as rational numbers. All right, so this is all for this lecture. As usual, like, comment, share, subscribe.